The sampling distribution has implications for finding the probability of an interval of realizations of the sample mean. The central limit theorem tells us that if n is big enough, the distribution of sample means is normal. So we can use the normal distribution to find the probability of an interval of y bar. How do we find the area under the curve between a and b? Usually I'd say with an integral, but this is the normal distribution and the integral of the normal PDF is gross. We use a standard normal table instead. We convert values on the y bar axis, our original normally distributed random variable, to values on the z-axis using a z-score. The standard deviation in the denominator of the z-score reflects the standard deviation of the sampling distribution, sigma over root n. So the z-score is y bar minus mu divided by sigma over root n. A quick example. Let's say the inside diameter of a randomly selected piston ring is a random variable whose distribution has mean value 12 centimeters and a standard deviation of 0.1 centimeters. Those are population parameters. What is the probability that the mean of a sample that we pull from that population of piston rings will be between 11.97 and 12.02 centimeters when the sample size is 42? The sample size of 42 is bigger than the magic number of 30. So we assume that the distribution of the sample mean is normally distributed, regardless of what the original distribution was for the inside diameter of piston rings. 11.97 on the y-bar axis equates to -2 on the z-axis. That is, 11.97 is 2 standard deviations below the mean of 12 centimeters. Likewise, the value 12.02 on the y-bar axis is 1.33 on the z-axis. And now we can use the z-table to find this probability. And the probability that z is between -2 and 1.33 is 0.8855. That is, if we take a sample of 42 piston rings, the probability that its sample mean inside diameter is between 11.97 and 12.02 centimeters is 0.8855. Or 88.55% of samples of size 42 will have mean inside diameters between 11.97 and 12.02 centimeters. But we may not just be interested in sample means. We might also be interested in proportions, for example. That is, what's the proportion of successes that we might see in a sample from the population? First, the population proportion P is obtained by taking the ratio of the number of successes, capital Y, we see in a population to the total number of elements in the population, capital N. Of course, we may not really know the population proportion, so we have to sample. The sample proportion, P hat, is similarly calculated as the ratio of successes, little y, in the sample to the number of elements in that sample, little n. And just like we saw with sample means, there's a distribution for the sample proportion P hat, because the proportion of successes in a sample, as you might guess, depends on the sample that we choose. We could get several different P hats for several different samples. So how do we describe the sampling distribution of P hat? The mean of the sampling distribution, mu sub P hat, is equal to population proportion P. And the standard deviation of the sampling distribution for P hat is denoted by sigma sub P hat. And we use the binomial distribution to help us with its calculation. You may remember that the standard deviation of the binomial distribution is the square root of P times 1 minus P divided by N. That's the standard deviation for the sampling distribution. The central limit theorem allows us to assume that the sampling distribution of P hat is approximately normal for a sufficiently large sample size. So, P hat is normally distributed with mean P and standard deviation square root of P times 1 minus P divided by N. Let's take a look at a proportion example, dealing with the bridges in Oklahoma that are considered to be a part of the national highway system. There are 3,300 such bridges, and 555 of those were deemed structurally deficient in 2014. So if we define our population as the National Highway System bridges in Oklahoma, then we know exactly what the proportion of that population that is considered structurally deficient, 555 out of 3,300, or 0.168. Let's say we'd like to characterize the probability that a sample proportion chosen from a sample of 350 bridges from the population will lie between 0.175 and 0.205. That is, what's the probability of the interval 0.175 to 0.205 on the P hat axis, the axis of the sampling distribution for the proportion? The z-score has the same setup. How different is the value on the axis from the mean in standard deviation units? Converting 0.175, we get 0.175 minus 0.168 divided by the square root of p times 1 minus p over n, which is 0.35. And we convert 0.205 in a similar way, finding that z is 1.85. So the probability that p hat, the sample proportion collected from a sample of 350, lies between 0.175 and 0.205 is equal to the probability that z lies between 0.35 and 1.85. And if we use our z-table, or Excel magic, we find that probability to be 0.331. That is, we estimate that 33% of our samples of size 350 bridges will have a sample proportion between 0.175 and 0.205. So we've taken our knowledge of sampling distributions and the central limit theorem and turned that into an ability to find the probabilities of intervals on the sampling distribution using the standard normal distribution. This is an important step in the methods of statistical inference that we'll discuss in later videos.